Basically, I'm trying to find out how it really makes sense to me as a child. So the topics that I explore are always based on what I think didn't get correctly explained to me at school, or alternatively, didn't get correctly transmitted over time from one culture to another. The title of my talk here, as you can see, is Links Between al-Khwarizmi's Method of Multiplying and Dividing Fractions and Brahmagupta's Arithmetic. This area of investigation is entirely because of my experiences as a child in class 6, as you'll see in this presentation. It's going to be a short presentation. It's going to be quite simple. Dividing fractions, don't ask why, just invert and multiply. That's a little similar to a mnemonic device that people have been using to know what to do when dividing fractions. Now, I continue it on. Just be careful if you try. Some say into, others by. The reason I say that is that I have an international audience who might see this. And in the West, when we say into, we mean divide. In India, into means multiplication. In the West, by usually means multiplication. However, in India, by means divide. So I just mentioned that because I'll be using the Indian tradition of into being multiply and by meaning divide. Here's my personal guru, my hero Brahmagupta, and he wrote his work on Ganita, or arithmetic, in 628 CE in his Brahmagupta Siddhanta in chapter 12. Around about 200 years later, al-Khwārizmi wrote a book, which is a book of Indian computation, or basically it's arithmetic done the Indian way, using 0 as a placeholder, and in the Latin version it was known as Algoritmo de Numero Indorum. So the Arabic world definitely did credit the new arithmetic that they were embracing to ancient Bharat, India. It's known as Dixit al-Khwarizmi, which means al-Khwarizmi said, from line 1 of the text. The original Arabic is lost, and yet we know the contents from copies of Latin translations. Now, unfortunately, the manuscript held by the Cambridge University Library was and is incomplete. So the previous translations of al-Khwarizmi's arithmetic, based on India's arithmetic, only about 60% of it was ever translated into English. So when I was wanting to explore the meaning behind that law or that rule, ours is not to reason why, just invert and multiply, I thought I'd start to search back in time to see maybe where it arose, and more importantly, what really is going on behind that rule. So the Cambridge University manuscript unfortunately stopped at al-Khwarizmi's explanation of 3.5 into 8 3/11. My research is informed by my own experiences and also my intuition that I've had for over half a century that somehow the foundations of elementary mathematics are not quite right. So I had that intuition, which is why I've been researching mathematics to try and find out how it seemingly went wrong and became filled with contradictions and paradoxes that are usually covered up by the use of laws and rules. So in 1972, in class 6, I was shown how to do the arithmetic of fractions. I could do fraction multiplication, yet never really understood it. Here is an example of my homework from 1972. You can see I've got additions of fractions, subtraction with fractions, multiplication of fractions. I don't exactly really know why I kept all of my mathematics books from when I was age 10, but they've certainly been very interesting for me to go back to. You can see that I got lots of ticks on my homework, but that means I don't necessarily understand what's going on. I am basically a robot parroting back what I'm told by my teacher. I'm learning procedures, but I'm not necessarily gaining understanding. And so much of my mathematics education at school was based on rote memorization of laws, rules, and formulas, and yet I didn't have a deep-seated intuition of what was exactly going on in the mathematics. Unfortunately, most mathematics education doesn't have that deep-seated true intuition to be able to explain exactly what's going on in the mathematics. We've got here 1/2 into 1/2 equals a quarter, and that's very simple for children to understand, because if I've got half of half a pizza, I know that I've got a quarter of a pizza. And so, yes, we usually have simple geometric diagrams that help us understand the multiplication of fractions. And I could see in my homework from when I was age 10 in class 6 that A by B into C by D equals AC by BD. I kind of knew that, and I knew how to multiply those fractions, but I didn't really understand the reason why this worked. So I'll present a geometric explanation of fraction multiplication. So I'll take for this example 2/3 into 3/4 equals 6/12. Here's a geometric instantiation, which you are probably familiar with. It's very, very basic, but I'm trying to situate this in a historical context. So here we've got a rectangle, and what we can do is we can partition this shape into 3 narrow strips. And I say partition because back in the medieval times in the West, partition was often used instead of the word division. Here we've got 3 equal thirds of that shape. Similarly, what we can also do is we can partition that same shape into 4 equal vertical segments. Altogether, when we partition both horizontally and vertically, we can see that we have 12 equal parts of that one quantity. Let's look at 2/3 of that quantity, and we can take 2 of those 3 equal parts. Similarly, we can take 3/4, and we can take 3 of the 4 equal parts. Altogether, when we look at the overlap of 2/3 into 3/4, we can see that the area of overlap changes into a green color, and if we count up those individual parts, we see that there are 6 parts out of the 12, and that gives us a geometric interpretation of that equation. That's what we do today, but how did al-Khwārizmī explain fraction multiplication using India's base 10 system? Now, I say base 10 here because he really only starts to explain fraction multiplication and division in base 10 in the part of the book that wasn't translated into English previously. Fortunately, a complete manuscript of Dixit al-Khwārizmi was found in the Museum of the Hispanic Society of America in New York. This complete Latin manuscript of al-Khwārizmi's explanation of Indian arithmetic was published in German in 1997 by Professor Menso Folkerts. Al-Khwārizmi's method of multiplying and dividing fractions in base 10 is now presented in English for the first time. I refer you to the paper prepared for this conference, which provides the original Latin, more detail, and the English translations in full. Here we've got al-Khwārizmi discussing the multiplication of mixed fractions. In this instance, it's 3.5 into 8 and 3/11. What I'm going to do, I'm going to give you the translation of the Latin text, and soon, after a couple of slides, you'll start to see some images, so you'll see how the numbers start to look visually. So just bear with me while I go through the translation of the Latin. So this is al-Khwārizmi speaking now. So if you want to multiply 3 and 1/2 by 8, and 3/11ths parts, write 3. Then put under it a 1, and under the 1, 2. And when you have done this, you have written down 3 and 1/2. Since a half is 1 part out of 2, just as a minute is a 60th of 1. So here you can see Al-Khwārizmi referring back to his earlier work in the sexagesimal system, base 60 system. Next, write on the other side 8, and under that 3, and under the 3, 11. And when you have done that, you have written down 8 and 3/11ths. So here we've got on the left-hand side, we have 3.5 presented in a way that's quite similar to the Indian tradition. And on the right, we have 8 and 3/11ths. So Al-Khwārizmi continues, and thus rewrite each of them according to the type in the bottom position, that is, the denominator. That is, you multiply the 3 by the 2, to which the 1 refers, and then add 1. These will be halves. So what's doing, he's got an integer of 3, he's going to multiply the 3 by the halves to get 6, and then add the 1 extra half to get 7 halves. So there are 7 halves which you write in place of the 3 and cross out the 3 and the 1 which is beneath it. What we're seeing here is we're seeing the gobar or the dust board treatment that was used in India being continued on in the writings of Al-Khwārizmi. So the 3 and 1/2 is then changed into the form of 7 halves. Also, you multiply the 8 by the 11, to which the 3 refers, and then add 3, and in this way you make them 11ths. So there are 91/11ths which you write in place of the 8, crossing out the 8 and the 3. So if I just backtrack a little, we see that the 3.5 into 8 and 3/11ths has now become 7 halves into 91/11ths. Next, you multiply 7, the halves, by 91/11ths, getting 637. And these are the types of parts of unity which are 20-secondths, and they are all of the same type. So we now have changed that into a different numerator entirely and a different denominator, and thus divide one of them by the other, and what results will be a whole number with a remainder of parts of unity of the type of the dividing number. And this is what you got out of the multiplication, 28 and 21 20-secondths part of unity. So here Al-Khwārizmi has gone through the explanation of 3.5 into 8 and 3/11ths equals a product of 28 and 21 20-seconds. And he's done that the traditional dustboard way of erasing out the workings as he's doing the calculations. So here we've got the standard form. You can see we've got 7 halves into 92/11ths gives us 637 20-seconds, and that's of the form, the traditional form, A by B into C by D equals AC by BD. And Al-Khwārizmi finishes off this section, and all multiplications of fractions goes similarly. We turn to Brahmagupta, and we read in chapter 12 of the Brahmagupta Siddhanta, integers are multiplied by the denominators and have the numerators added. Look on the right-hand side, and we see that Al-Khwārizmi is exactly following Brahmagupta's instructions. So for 3.5, Al-Khwārizmi multiplies the 3 into the 2 and adds the 1 to arrive at 7 halves, which is exactly Brahmagupta's instruction. Integers are multiplied by the denominator. So the integer is 3. It's multiplied by the denominator, which is halves, which gives you 6. And then you add the numerator, which gives you 7 halves. So for 8 and 3/11ths, Al-Khwārizmi multiplies 8 into 11 and adds 3 to arrive at 91/11ths. So Brahmagupta continues, the product of the numerators divided by the product of the denominators is multiplication of 2 or of many terms. And this is what al-Khwārizmi arrives at doing, because he simply then multiplies 7 halves into 91 elevenths to arrive at 637 22nds. So we can see a direct lineage from Brahmagupta's explanation of fraction multiplication. We can now see for the first time in the English language that al-Khwārizmi did exactly the same thing almost 200 years later. As I say here, Brahmagupta's and al-Khwārizmi's approach to the multiplication of fractions in base 10 is the same. When I was in class 6, I never really understood fraction division. So here we've got 2/3 by 3/4. And I was told at school, ours is not to reason why, just invert and multiply. That's the typical thing. My teacher once told me, Jonathan, don't worry so much about mathematics. Mathematics is only confusing if you think about it. I was actively encouraged not to think about mathematics and just to obey the rules. So here we've got 2/3 by 3/4 equals 2/3 into 4/3. So that's the typical approach that we're told to memorize. Here we can see back in 1972, I did as I was told. And if we look at that third example here of 1 7/8 by 2 2/5, you can see that I did exactly what Brahmagupta were telling us to do. I multiplied the integer by the denominator and added the numerator and then went through the process. So I then got 1 7/8 divided by 2 2/5 equals 15/8 divided by 12/5. But you can see in my homework that I then followed the rule of invert and multiply and got the correct answer through rote memorization. Now, my question is, did al-Khwārizmi invert and multiply when dividing fractions in base 10? Where did this originate from? Now I turn to the English translation for the first time of how al-Khwārizmi divided mixed fractions. And al-Khwārizmi has an example of 20 2/13 by 3 1/3. So what he does is he gets rid of the integer by converting it into the denominator. And so you can see that the 20 2/13 becomes 262/13, and the 3 1/3 becomes 10/3. So then what al-Khwārizmi says is now what we have to do is to get a common denominator between the two terms. And he does this by multiplying the 13 into the 3 to get a new denominator of 39ths. So he then creates a new expression of 786 by 39 by 130 by 39. And then because we've got a common denominator, he then simply says now we can just simply divide 786 by 130. And arrive at the answer of 6 and 6 130ths. Now, my question is, did al-Khwārizmi invert and multiply when dividing fractions in base 10? And the answer is he didn't. He did not invert and multiply when dividing fractions in base 10. So my question is, did Brahmagupta invert and multiply when dividing fractions in base 10? And let's see what Brahmagupta wrote from chapter 12 of Brahmasphita Siddhanta. First of all, both terms being rendered homogeneous. So he converts, in this example, 20 2/13 becomes 262/13. If I apply Brahmagupta's text to al-Khwārizmi's example, we see again that 3 1/3 is then converted to 10/3. Then Brahmagupta continues, the denominator and numerator of the divisor are transposed. They're inverted and multiplied. And then the denominator of the dividend is multiplied by the new denominator and its numerator by the new numerator. Thus, division is performed. So straight away, Brahmagupta goes into the invert and multiply solution. So he doesn't end up getting 39ths as a common denominator. He goes straight to 768 by 130. So if we compare the two approaches between Brahmagupta and al-Khwārizmi, you can see that al-Khwārizmi's got an extra step in his calculation where he converts the numbers, the terms, to have a common denominator of 39ths, but in Brahmagupta's method, where he does say and recommend to invert and multiply, that step is unnecessary. So we see that Brahmagupta had a more efficient algorithm for the division of mixed fractions than al-Khwārizmi. I'm still wanting to know, why does invert and multiply even work? And I'm aware I've got about another 4 minutes to go. So I believe it all stems back to the golden rule, the rule of 3. And I believe that's what's at the heart of multiplication and division. And this is also seen in Euclid's propositions about given 3 terms, find the 4th, which is in Book 6 of Euclid's Elements. So here we've got 2/3 by 3/4 equals 2/3 into 4/3. Why does this even work? Because that's why I began this exploration in the first place. Now, what I've kind of arrived at after decades of thinking and exploring in many cultures and many languages, in short, in multiplication, whatever we do to one to make the multiplier, we do to the multiplicand to make the product. As 1 is to the multiplier, the multiplicand is to the product. In division, conversely, with division being the inverse operation, whatever we do to the divisor to make 1, we do to the dividend to make the quotient. So as the divisor is to 1, the dividend is to the quotient. If we look at this example of 2/3 by 3/4, what do we have to do to the divisor 3/4 to make it 1? Well, we multiply it by its reciprocal. So that's what we do to the dividend to get the quotient. So that relationship, that proportional relationship, based on the relationship of the divisor to 1, is why we invert and multiply when dividing fractions. I got a very good from my teacher for doing my fraction addition, subtraction, multiplication, and division of mixed fractions. I got very good answers, but I did not get very good understanding until just a few years ago. So I now understand why invert and multiply works when dividing fractions, having investigated a lot of ancient works involving proportion, rule of 3 across many languages. So thank you for watching this short presentation.
Thank you, Professor Crabtree. Now the talk is open for discussion. Any question?